Good day, everyone. So, for today's lesson, we're going to talk about voltammetry and amperometry. But before that, we need to have a short recap. So, can anyone here answer this question? So, what is the main principle behind gravimetric analysis? Okay, thank you, Mister. So, let's make it more simple. Gravimetric analysis is a method used to find out how much of a certain substance is in a sample by measuring its mass. First, we add chemicals to the sample that cause the substance we want to measure to form a solid, called a precipitate. After the precipitate forms, we separate it from the liquid and dry it until it reaches a constant weight. By carefully weighing the solid, we can calculate how much of the original substance was in the sample. This method is very precise because it relies on accurate mass measurement to determine the concentration of the substance. Okay, thank you for participating. So, now, uh, we're going to talk about the objective of our lesson. So, our objective is at the end of this session, the students, which is you guys, are expected to describe the fundamental principles of voltammetry and amperometry, recognize and explain the role of key concepts in voltammetry and amperometry. And lastly, analyze voltammetric and amperometric data to determine the concentration of analytes. So, before we proceed to our discussion, I'm going to have you answer a four-item questions, and I'm going to give you 10 minutes to write it down on your paper. And after that, you're going to pass it to me so I can collect it and check it later. Okay, time is up. So pass it in front. So Miss President, can you give it to me later after our discussion? So now, let's proceed to the principle of voltammetry. So voltammetric techniques involve the electrolysis of the solution to be analyzed using a controlled external power source and measuring the resultant current potential or current time curves to obtain information about the solution. The species to be determined undergoes oxidation or reduction at a working electrode. The voltage between the working electrode and an auxiliary or counter electrode is controlled by the external circuitry in order to maintain a preselected potential difference at the working electrode. With respect to the reference electrode as a function of time, a typical voltammetric cell shown in figure 1 has a working electrode, reference electrode, and an auxiliary electrode and contains the solution to be analyzed. Often the solution is deaerated with nitrogen to prevent interference due to the reduction reactions of oxygen. If there is no reaction at the working electrode, the potential changes greatly for a very small increase in current. A mercury drop electrode, for example, has a polarization range between positive 0.3 voltage and negative 2.7 voltage against the SCE and in the absence of oxygen so that many reactions that occur in that range may be studied. By controlling the potential of the working electrode, a particular reaction may be selected. Suppose a cell has two inert, solid electrodes and a reference electrode which dip into a aqueous solution containing copper ions. In order to cause any reaction, the applied potential must exceed the decomposition potential. This may be calculated by considering the reaction at each electrode and adding the extra potentials or overpotentials due to polarization effect at the electrode and to the voltage needed to drive the current against the resistance of the solution. In this example, in order to drive the cell reaction, a voltage greater than about negative 2.54 voltage must be applied. This reaction that occur is Cu raised to the power of 2 plus H2O equal QUS plus 1 half O2 plus 2H plus. The copper is then composited on the cathode and oxygen is evolved at the anode. This is the basis for electrogravimetry, where the copper is completely deposited from solution and the increase in weight of the cathode determined. The analysis may be conducted using either a controlled potential or a controlled current. So, Clu- coulometric methods of analysis involve measuring the quantity of electricity and coulombs needed to convert the analyte to a different oxidation state. If the electrolysis occurs at 100% efficiency, Faraday's law may be applied and each 96,485 Celsius will bring about the reaction corresponding to 1 mole of electron transfer. I'm sorry, but to correct myself, it's 96,485 coulombs. So, going back to our discussion, for example, using a silver anode, the passage of a current produces silver ions which react with any chloride in the solution. Bromine and acids may also be generated coulometrically. Polographic methods employ a microelectrode, often a dropping mercury electrode (DME), as the working electrode, plus a reference electrode (SCE), and a mercury pool of auxiliary electrode. The simplest potential time regime, where the potential increases regularly, linear potential sweep DC voltammetry, is applied to the cell containing the analyte and a supporting electrolyte to carry the majority of the current. In this method, the transport of ions to the electrode depends on three factors: diffusion, convection or stirring, and conduction. The effects of conduction of the ion that reacts at the electrode is minimized by using a concentration of supporting electrolyte, such as KCE, about 50 times higher than that of the analyte. Stirring and convection are minimized. The result polographic curve shows three regions. Number one is if a potential difference is applied across a cell and no reaction occurs, only the residential current will flow. If the and number two, if the reducible ion says is present, it will migrate to the dropping mercury cathode. If the applied potential exceeds its decomposition potential, it will be reduced to the metal, which dissolves in the mercury. As the cadmium plates out, the layer around the electrode is depleted and more cadmium ions must diffuse in from outside through the diffusion layer of thickness. This will cause a current to flow which depend on the concentration gradient between the bulk solution and the surface. Eventually, the surface concentration becomes zero and the limiting diffusion current is reached. The constant depends on the number of electrode transferred. The diffusion coefficient of the ion is the solution and the characteristic of the cathode. Number three, if the potential is increased further, the current does not increase unless the reducible ions are present. These three regions are shown in figure 2. The half-wave potential is usually quoted relative to the SCE, and like the standard electrode potential, is characteristic of the electrode reaction. Typical values are shown in table 1. Okay, and now let's proceed to instrumentation. For most voltammetric and amperometric methods, the instrumentation includes a working microelectrode, a reference electrode, and an auxiliary or counter electrode, together with electronic equipments to control the voltage and voltage sweep, plus a computer or recorder to collect data. The earliest electrode used was the dropping mercury electrode, which is DME. where pure mercury flows through a fine capillary either due to gravitational force or by applied pressure. Drop times of a few seconds are usual. This electrode has the advantage that the surface area is small and is constantly refreshed so that products of electrolysis do not accumulate. Number two, mercury has a high overpotential for hydrogen formation, which allow the reduction of other species. Other electrode used are the static or hanging mercury drop electrode, where the drop is dislodged at a particular time and size, and solid microelectrodes such as platinum and glassy carbon, which may be incorporated into a rotating disc electrode. Dissolved oxygen in the sample solution must be removed, since oxygen may be reduced in two steps, giving waves that overlap with those of the sample. This is usually done by passing oxygen-free nitrogen through a sample solution during the experiment. Maxima on the waves are due to surface effects and may be surpassed by adding a small amount of surface active agents such as gelatin or Triton X100. Anodic stripping voltammetry is designed to measure trace amounts by preconcentrating them onto a suitable electrode. The experiment has two stages. Number one, the sample is electrolyzed onto a hanging mercury drop or a mercury film deposited on a carbon electrode. By Faraday's law, topic C2 passing a current of amps to second will produce a concentration in a mercury film of thickness. Number 2, the reduced species, that is, the metal, is the oxidized out of the film by making the electrode increasingly anodic. A peak appears on the current potential plot, and the peak current can be shown to be where the constant K includes the diffusion and other constant, and N is the rate of increase of the anodic potential, the big potential at which an active species is oxidized and characteristic of that species, and is close to its half-wave potential. So that is the instrumentation, and now we're going to proceed at the application. Polographic techniques may be used in both qualitative and quantitative mode. Since the half-wave potential is characteristic of the particular reaction that is occurring at the potential, it is possible to identify the species involved. A simple case is shown in Figure 3, where a mixture of metal ions was analyzed. The two reduction waves for copper occur at negative zero point 0.1 and negative 0.35 voltage, cadmium at negative 0.69, nickel at negative 1.1, and zinc at negative 1.35 voltage. This illustrates an analysis that may identify the species qualitatively, and by using a standard addition method can also determine the ions quantitatively. Organic substance may be determined either in an aqueous or non-aqueous medium. For example, the concentration of nitrobenzene in commercial aniline may be found by studying the reaction. The oxygen electrode is based on voltammetric principles and depends on the diffusion and reduction of oxygen. It is also called the clock sensor. The cell has a lead anode and a silver cathode set close together in an alkaline solution. Often 1 mKOH at the anode, the reaction is the silver cathode is inert, unless oxygen or another reducible species can diffuse to it. A semi-permeable membrane through which only oxygen can diffuse surrounds the electrodes, and then the reduction reaction takes place. Since the current depends on the diffusion of the oxygen to the electrode from the external solution, and this diffusion is proportional to the concentration of oxygen in the external solution, this electrode may be used to measure dissolved oxygen. Amperometric titration are used to determine substance by measuring the limiting diffusion current of a species as a function of the volume of a reagent added to react with the species. Since current is proportional to the concentration, it will decrease as a species is used up, or increase as the excess of a species becomes greater. Application of anodic stripping voltammetry are chiefly for the determination of trace amounts of anal gum-forming metals, while cathode stripping voltammetry is used for determining species that form insoluble salt with mercury. The pro-concentration stage allows determination in the concentration range 10 raised to the power of negative 6 to 10 raised to the power of negative 8. And that's all for our topic about voltammetry and amperometry. Does anyone have questions? Okay, thank you very much. And for our activity, you're going to answer this scenario and for 10 minutes, and you're going to pass it to me so I can correct it, check it, and record it. So I'll give you 10 minutes. Okay, time is up. Thank you everyone. So for your take home task, which is also going to be your performance task, we're going to do a activity which you are going to analyze using voltammetry and amperometry. This you are going to pass it to our next session. So thank you again for participating and listening to our lesson. Uh, Please clean your classroom before leaving. Thank you, everyone. God bless.